We finished a series of lectures on interactions, thermal and mechanical. There's really one other type of interaction to talk about. That's called a diffusive interaction or diffusive equilibrium. And it's a matter of taste as to where you incorporate this topic into a series of lectures. This, for me, is a nice way to segue between thermal and mechanical interactions and topics such as thermodynamic potentials and then phase equilibria and phase transitions. So this is sort of on the cusp in between those two ideas. What do we mean by diffusive equilibrium? Let's show it by this example. Suppose I have the old, maybe a system of two gases, whatever the case may be, system A and system B, and maybe system A has an energy E sub A, and has a number of particles, N sub A, and an entropy, S sub A, and system B is the same. Energy B, number of particles, B, and S sub B would be the entropy of system B. So let's let the two systems interact by exchanging particles. Okay, this is different. We have not covered this sort of interaction before. This is what we call diffusive interaction. Let's hold the total energy and total number of particles fixed. So Na and Nb can change, but the sum will always be a constant. Same thing with the energy. The total energy, because we're calling it E in this case, is Ea plus E. Those two quantities will not change. So in equilibrium, we expect that the total entropy would be a maximum, which is to say, I can say that the partial of the total entropy with respect to the energy of A would be equal to the partial of total entropy with respect to the, I should say, E sub B, which of course implies that the temperature of A is equal to the temperature of B. We're in thermal equilibrium. It should be, I should say that this is, these two have to be equal to 0 if we're in a maximum condition. So that being the case, since we're also in equilibrium, we're going to say that we are likewise in diffusive equilibriums, which says that the partial of SA with respect to Na is equal to the partial of SB with respect to NB. And oftentimes what we do, so this would be at fixed energy and volume. That being the case, I like to multiply, for convention's sake, each term by t, by minus t in fact. So minus t dSA Na is equal to minus t dSB dNB at equilibrium. And I define the quantity minus t ds Bn at constant energy and volume as the chemical potential, mu. I know we use mu an awful lot in physics. This is yet another great use for it. So in diffusive equilibrium, it must be that the chemical potential of A must be equal to the chemical potential of B. So we go through this again. In thermal equilibrium, the temperatures are the same. If we talked about mechanical equilibrium, the pressures would be the same. Now in diffusive equilibrium, the chemical potentials are the same. If the systems start out with different values of chemical potential, what will happen is the system with the larger value, ds, dn, or the smaller chemical potential, is going to gain particles from the system with the larger chemical potential. So a system with higher chemical potential will be prone to giving up particles. A system with lower chemical potential will be prone to receiving particles. Well, what this all does is it takes the expression that we had before, what we would call the so-called thermodynamic identity, and I'm going to modify it. So we started with du TdS, that was my heat term, and minus PdV was my work term. I'm going to have another term to add to it, and that is the term that goes with my chemical potential. I can generalize my thermodynamic identity in the following way. I can write ds in terms of dE. I can write it in terms of dV, holding number of particles and energy constant. And then times dV plus ds dN at constant energy and constant volume times the n. So this is a generalized statement of the general thermodynamic identity. So in a process where entropy and volume are fixed, we can say that the energy dE is mu dN. Or, turning it around, I can say that chemical potential can be described as the partial of energy with respect to n holding volume and temperature constant. So this tells us quite a lot. First of all, it tells us that the units of chemical potential must be the same as the units for energy. It also tells us that the amount that a system's energy changes if a particle is either added or taken away from the system. So if the entropy and volume remain fixed, you have to either remove some energy to add a particle, if the chemical potential is negative, or add some energy to add a particle if the chemical potential is positive. Let's do an example of this. Let's go back to our old friend, the Einstein solid. So let's just say that we have 3 oscillators, and we have 3 units of energy to go around. Of course, if you do figure out the omega, the total number of accessible states in a case like that would be 10, and therefore the entropy would be k log of 10. Suppose I want to add another oscillator. Now we know this isn't logical because each oscillator, remember, is only a third of a particle, since we talk about one particle having 3 oscillation directions, but be that as it may, this is just for example's sake. If I add another oscillator, omega now, so if I have 4 oscillators, omega goes to 20. And my new entropy is equal to k log of 20. But suppose we want to keep entropy fixed when we add the oscillator. Well, to do that, we could remove a unit of energy. That's the way we would keep the entropy fixed. Let's just say the value of 1 unit of energy is E. So we'll define E as 1 unit of energy. So I can say my chemical potential is equal to my change in energy divided by my change in number at constant entropy, which is going to be equal to minus E, because that's what I'm removing. My entropy stays constant. I'm sorry, I'm removing one particle, and that, of course, is equal to minus E. So that would be my chemical potential. As I say, it's a little, the example's a little bit silly because you can't just remove one oscillator, since we consider each particle to be having 3 oscillators, one in each of the 3 directions. Be that as it may, there's maybe a more realistic example. Another favorite of ours, it's with the ideal gas. You might remember we have an equation called the Sackur-Tetrode equation to calculate the entropy of an ideal gas, and it looks like this. It's rather hideous looking, but we'll put it up there anyway. Okay, there's the expression for the entropy of an ideal gas. If I want to take the partial of S with respect to N to get the chemical potential, that's going to be equal to minus T times K. We'll write it this way. Skip a step. Minus KT log E over N. 4 pi m u 3n h squared, the 3/2. And since for an ideal gas, the energy by equal partition of energy theorem for 3n degrees of freedom is 3/2 nkt, I can write my chemical potential as minus kT times the log of 2 pi m kt over h squared. This quantity to the 3/2 times V over N. So this is my chemical potential for an ideal gas at temperature T. So if I'm at room temperature, suppose I'm at room temperature, 20 degrees Celsius or so, and 1 atmosphere of pressure, then I'm going to get V over N is about 4.2 times 10 to the minus 26 cubic meters per molecule. And so, in this case, the quantity h squared over 2 pi m kt to the 3/2 is much smaller than that. So in this case, then suppose we have helium. Let's use helium. For helium, we have 1.3 times 10 to the minus 3rd cubic meters per molecule. That being the case, if I work this on through, I will get the product of my log in here. If I put my numbers in here for for helium, I should get something on the order of 12.7. And so the chemical potential then for helium would be minus 0.32 electron volts if I play all this through. So this is kind of interesting. If the number per volume increases while the temperature is constant, chemical potential becomes less negative, so the gas is more willing to give up particles to a nearby system. Suppose we have a mixed system. Suppose you have air. So you've got nitrogen and oxygen and air. We get separate chemical potentials. So I can write it minus T ds dn, constant energy, constant volume, constant number of the second molecule, where mu2 would be minus T dN1, ds dN2 at constant energy, volume, and number of particles for the first substance. So in general, we can once again modify our thermodynamic relation just slightly. I can write that then in probably about the most general way. I can write this as du, or dE, we're using energy, du equals CdS minus P dV plus the sum of all of my diffusive equilibrium terms, mu sub I, dN sub I. We use chemical potential for a number of reasons. One, to study chemical reactions, which we probably won't do very much in here, but to study phase transitions, very, very important for that, and then also to study quantum statistics and all of the exotic behavior that goes with quantum statistics. So stay tuned. We will be using the chemical potential quite a bit. So we do a very lovely summary chart here to sort of wrap up this talk of interactions. And so we can talk about a thermal interaction where the exchange quantity is energy, the governing variable is temperature, and of course the equation is 1 over T is equal to ds dE at constant volume and number of particles. For the mechanical interaction, the exchange quantity would be volume, or any external parameter. The governing variable would be the pressure, and then of course the equation for it would be ds dV at constant energy and constant number of particles. And finally, diffusive equilibrium, or the diffusive interaction, the exchange quantity is going to be number of particles. The governing variable will be the chemical potential, and then the equation is 1 over T is ds dN at constant E and constant V. So it's a nice way to summarize this. The use of microscopic to derive macroscopic in this case is what we call statistical mechanics. That's where we're going to stop. Next time we're going to talk about a number, or several more, thermodynamic potentials before we move into phase transitions. Thank you.